Hey, Intro to Calc, and welcome to our second week of conic sections. Last week we got a quick, brief introduction or reintroduction to the circle, and this week we're going to fill in the rest of our conic sections the parabola, the ellipse, and the hyperbola. You may not have seen these since Math 2, so put your 10th grade brain back on. Definitely saw the circle and the parabola back then, and you may not have even seen the ellipse and the hyperbola, but they all kind of have some things in common. If you have not already tried to fill in these notes yourself, pause the video now and just fill in as much as you can. What do you think these arrows are pointing to based on what you've seen in Khan Academy already, or what you might remember from a few years back, or maybe just last year in math? So pause the video now and give that a shot. I'm going to go ahead and dive right into the circle, the one you're already familiar with. And for each of these shapes, I'm going to go through the identifying features or those key features and write out the formula. So let's start with the circle. The first thing that's going to be the same across all of these conic sections is that center point. So this point right in the middle for a circle, it is called the center, novel concept, and it's at some coordinate h, comma, k. So just like you might have seen with every other function we've ever looked at, hk is kind of the starting point or the center point for our function. H comma k would be h the x coordinate, k the y coordinate. And this right here is the main defining feature of a circle, and that is the radius. The definition of a circle is a set of all points equidistant from the center. Well, this is that kind of distance when we say equidistant from the center. So if we know the center and we know the radius, let's write out that formula. So all circles are going to have this same setup. X minus something squared plus y minus something squared equals something else squared. It's x squared, y squared equals something squared. Well, what are those somethings? Well, x minus h, the x coordinate of the center, y minus k, the y coordinate of the center, equals the radius squared. And if I can give you a little forewarning, the one mistake I see made over and over and over is right here. Be careful, this is not just equal to the radius, it's equal to the radius squared. The radius squared. So if we find out that the radius is 4, it's equal to 16. If you find out that the radius is 3, it's equal to 9. So be careful with that. That's the one mistake I see pretty often. Okay, guys, that's the circle. Let's check out the ellipse, because that's actually really, really close to the circle. I like to think of the ellipse as a circle whose center has split off. The center has kind of morphed into two different centers. So we're going to look at two formulas for the ellipse, and there's a really minor difference between these two, but it's still worth our time to talk about both of them. So let's start with the same exact thing as our circle, and that is our center. And we're still going to use h, comma, k, meaning the x coordinate and the y coordinate of where it is actually centered. But instead of us having just one center or one point that everything is equidistant from, we have two, and we're going to call each of those a focus point. So this right here is a focus, and this right here would be our second focus point. Those points aren't really helpful in creating the graph though, so that's where these other points come from. The points that actually create our graph, that actually tell us the boundaries of our ellipse, are going to be our vertices and our co-vertices. So this one right here is a vertex. This one would be the second vertex. That's always going to be the longer of the two. We call that the main axis. The longer of the two is going to be our vertex, and that leaves this one to be our co-vertex. The shorter of the two is always going to be called our co-vertex. So A will extend us to the vertex, that's going to be the larger of the two numbers, and B will extend us to the co-vertex, that's going to be the smaller of the two numbers. So let's write the formula out for this one. So this also has some kind of like standard form, and it looks a lot like a circle. X minus something squared, y minus something squared. But this one is always going to equal 1. It's always, 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 always going to equal 1. And that's because I like to think of it as a circle with two different radii. There's a radius that extends in one direction, that's A, and there's a radius that extends in the other direction, that's B. So we can think of them having their own radii. There's like the horizontal radius and the vertical radius. So where do we fill in these numbers? Same thing. H goes right here, K goes right here, because we're talking about shifting it over H and shifting it up Y. And then what is our X radius? Well, how far do we extend in the X direction? That's A, the larger of the two numbers, A squared. And how far do we extend in the Y direction? That would be B, in this case the smaller of the two numbers, to the covertex. So there we go. That is our equation if we're looking at this horizontal ellipse. Now let's transfer that over to vertical. Maybe pause the video right now, see if you can fill this in without my help, and then turn it back on and see if you got it all right. The center is the same, h comma k. The longer of the two sides connects us to our vertex. The shorter of the two sides connects us to our covertex. And our focus point is always along the longer side, or along what we call the major axis. It's always along the major axis. So this is our focus point. And this would be that second focus point on the other side. So I'm going to kind of put that in there on major axis. And major meaning longer. It's always on that longer major axis. For a lot of these, if you were to try to plot the focus along the covertex line, it would end up outside the ellipse, and that doesn't work. So let's put the equation together. Same exact starting point. We have our x minus something squared all over its own radius plus y minus something squared over its own radius equals 1. It's always going to equal 1. We still fill in h and k because that is still the horizontal shift and the vertical shift. But now, if you notice, the larger of the two vertices, if you want to think of it that way, the larger of the two distances from the center is y. So that larger number goes underneath the y, and the smaller number goes underneath the x. So the main difference between these two, the horizontal and vertical, is that if the larger number is underneath the x-coordinate, you're going to see your ellipse extend outward along the x-axis in that x direction. If their larger number is underneath the y-coordinate, you're going to see it be taller and thinner, extending along the y-axis or in the y direction. Cool, that's an ellipse. Let's talk hyperbolas, because they're actually pretty close to ellipses. We still have the center. Like I said, this thing is the one thing that stays constant. I'm going to mark both of them as center. And a lot of this does look the same. We still do have our focus points right here at C. We still do have our vertex right here at A. See that? Vertex is A. That would be our second vertex right here. And we still do have a co-vertex here at B. So all of that still applies. If I kind of compare it to ellipse really quickly, A goes out to my vertex, A still goes out to my vertex. B goes to my co-vertex, B still goes to my co-vertex. C goes to my focus, C still goes to my focus. But if you notice here, the focus does actually extend outside. It's not trapped inside of this little elliptical shape. It extends outside. And that's actually what makes this into a hyperbola instead of an ellipse. The last feature to notice is these dotted lines here, and since we've started back in Math 2, I think, they mean the same thing. They're asymptotes. And our hyperbolas will always have those two asymptotes. So let's see if we can write out this formula. Believe it or not, it's the same exact pattern. Same exact pattern. We have x minus something squared over kind of its radius, or that's extension from center. And we have y minus something squared over its radius, or whatever it extends out from center, equals 1. This looks very, 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 very similar, but here's the main difference, guys. This is subtracted. This is subtracted. How do I know which one is subtracted or which one's positive, which one's negative? Well, whatever direction our focus lies on, if you notice, our focus follows this x-axis or this horizontal direction. That is going to be our leading term. So if I find the focus along the x, that is my leading term. So now we're going to fill in everything almost exactly like we did for the ellipse. Our center is at HK, and whatever distance we extend in the x direction goes underneath x, and whatever distance we extend in the y direction goes underneath y. So pause the video, try the other hyperbola equation. Pause the video and try the other hyperbola equation. Okay, how'd you guys do? If you notice, x is still subtracting h because that's still the horizontal shift. Y is still subtracting k because that's still the vertical shift. This is still the distance from center in the y direction up to the vertex. This is still the distance from center in the x direction out to the co-vertex. And y is now our leading term because we're along the y-axis, or we're in this vertical up and down motion. So one last detail to fill in for the ellipse and the hyperbola is, how do you find C? How do I find this magic focus point? Well, they're both versions of the Pythagorean theorem, but there's a minor difference in them. So when I think about the ellipse is looking for a smaller number that is inside, that's inside the ellipse itself. It's looking for a smaller number inside the ellipse. So how we're going to solve this is say that c squared, that's our distance to the focus, is a squared minus b squared, because we're looking for the smaller side of the triangle, essentially. We're trying to find the smaller side of this right triangle that fits inside of our ellipse. Well, the hyperbola is just the opposite. We want that focus point to now be outside of the shape, outside of the vertices and co-vertices. So that means we're looking for the longest side of our triangle in this Pythagorean relationship. So our c squared just equals a squared plus b squared. Okay, last but not least, our parabola. And I'm warning you guys now that if you're thinking about the parabolas that we've looked at more recently, this format is totally different. Same parabolas, but a different way to think of the equation. We still have a center. We still have a center, but instead of calling it a center with a parabola, we just call it a vertex. It means the same thing. It is still kind of that center starting point of our graph. We still are going to use h and k to define where that center, now vertex, is. Just like the hyperbola, we have a focus And that focus is kind of in a similar place as the hyperbola. The only other thing you might actually remember is that there is this thing called an axis of symmetry. And it's right there in the name. It's that line you can draw that is a line of symmetry for your graph. So when we're talking about a conic section parabola, vertex and axis of symmetry, we're already familiar with those, but now we have this thing called focus and directrix. Focus and directrix. The focus is that point that your parabola is going to kind of wrap around. The directrix is this straight line that your graph repels away from. So again, the focus is what it kind of wraps around, and so you can think it's like actually getting closer to the focus as it kind of goes away, and the directrix, it is getting farther and farther from the directrix as it goes. It's kind of repelling away from the directrix. So how does this look in an equation? So this is a traditional parabola, but we're going to write it a little bit differently. We still have x minus something squared equals 4, because that's this ratio that we've developed, y minus something. But if you notice that y is not squared, that's normal for a parabola. In a parabola, the y isn't squared, the x is squared. So let's fill in the blanks here. H is our horizontal shift to our vertex or our center. K is our vertical shift to our vertex or our center. Now P is going to be this kind of ratio that we've developed that tells you how far away the focus and the directrix are, how far away they are. I want you guys to imagine as this focus pulls further and further and further away, this parabola becomes wider and wider and wider. As we move these closer together, so let's say we put them really, 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 really close, the parabola becomes narrower and narrower. So if you want to give yourself a little check, see if you can fill out the other parabola. See if you can fill out this new kind of rotated, different style of parabola. Pause the video, try it now, and check back. So I'm going to talk through the equation. The equation looks almost exactly like the one we just did, but here's the deal. Our parabola is no longer the traditional parabola we're looking at that turns upward or turns downward. This parabola would turn either left or right. And so what we've done is we've taken the inverse. We've kind of turned this into a square root function instead of a squared function. And that's because the y in this case is squared. The y is the term that's squared, and the x is the term that's not squared. So if we look at these side by side, we really have just switched the x and y's position. That's all we've done. We've just switched the x and y position. Everything else is the same. K is still modifying y, that's the vertical shift for our center or our vertex. H is still modifying x, that's the horizontal shift. And P is still that ratio or that distance from the vertex to both the focus and the directrix. So 2 units this way, 2 units this way. If P was 1, it would mean 1 unit this way, 1 unit this way. If P was 15, gosh, we would never graph that, but it would be 15 units this way, 15 units this way. So one last little detail with parabolas I want you guys to figure out and add to your notes is, how will I know if a parabola is pointing up or down? That would be on this one right here. How do I know if that's pointing up or down? And then what about this one? How do I know if this one should be pointing left or right? I want you guys to figure that out. Maybe add a little note below. You've got some space down here to add a little extra note about how you know whether it's left, right, up, or down. And then come to office hours if you want to verify that, check it, or get a little extra help. So there you go, guys. There are all the notes you need for the rest of our little Conic sections module. Use these as you're doing your Khan Academy. Use these as you are doing everything you're working on, including your project. And definitely come to office hours for some questions.